All right, so we're going to talk a little bit about effect sizes, confidence intervals, some of the things that we learned last week, and then we're going to go ahead and talk about ANOVA, and hopefully this will help you guys, in addition to the readings, this will help you guys understand the concepts a little bit better. Let's talk a little bit about standard error of measurement, or SEM. So the belief is that if you have any sort of score or number that you're going to take multiple times, or the mean, whatever it is, it will fall into a normal distribution because you're sampling from the population. And so you don't have the exact mean from the population, you brought in a sample. And so if you sampled over and over different groups from that population, that they would eventually fall into a normal distribution. And so the SEM is the standard error. And that's what you'll see a lot in SPSS output, the standard error. And so that's assuming this normal distribution of this sampling distribution, then you would actually use it just like you would a standard deviation. Or 68% of the time, the data point would fall within one SEM below and above, and 95%, and then the 99.5. Now, because the standard error of measurement is considered a measurement of error, right? How much error you have in actually having the exact number. You want a small SEM. And they talk a lot about how you could calculate the SEM based on a normal distribution, but often what's used is the t distribution, because the t distribution is based on sample size. All right, so that's the standard error of measure, and the reason you need to know that is because you're going to see it a lot in your SPSS output. Okay, so let's quickly talk about confidence intervals. And confidence intervals can be calculated for any of your descriptive statistics. They talk in the book about calculating them for means, and they also can be calculated for effect sizes, which is what they talk about in the Ellis text. And we're not going to talk about calculating them as much, but I just want you to understand the concept because, again, you're going to get a lot of these in your SPSS output, and you're also going to see confidence intervals in journal articles when you're reading about research. And so it's basically the estimated range of values that has the probability of containing the actual value. So normally researchers will report a 95% confidence interval. And so basically that they're stating they're 95% confident that the actual statistic, whatever it is, lies within the upper and lower limits of that. And usually that's plus or minus 2 standard deviations from the mean. And you will see this a lot in what they talked about with polling, right? And they'll talk about the margin of error. That's what they're talking about, is they have a certain number of confidence. And again, you want your confidence error to be smaller if you're using SEM, right? Because that's less error. And you would want it to be smaller so that way you can say within confidence it's within a certain numbers and you don't want it to be as wide. Okay, power and effect size. Okay, so we talked about this a little bit last week, but I wanted to go back and clarify and make sure that you guys understood what statistical significance is. And statistical significance means that this is the certainty that what the finding is not due to error, that the finding is correct. And so very classic p-value, right? Your statistical significance is 0.05. And so that means that you have 95% certainty that the finding is correct. And that protects you from your type 1 error, right? Type 1 error is rejecting the null when you shouldn't be rejecting the null. The larger your sample size, the more likely you are to have a statistically significant finding. But, and we talked a little bit about this in the webinar last week about how if you have a huge sample size, then everything's going to be significant, and that can be an issue in itself. And so we know that what this says about making sure that, yes, this is significant, and we know it's not due to chance, but the bottom line is we don't know, other than that, we don't know what that means. And so that's why we talk about effect size. So effect size is our practical significance. So it's not just, yes, this is significant and not due to chance, but it's also how meaningful is this? And that's what's really helpful of that, is that it looks at the sample size and then tells you about how meaningful it is. And so this is related to statistical power. And so statistical power is like the opposite of statistical significance, because this is looking at type 2 error rate. So we would want an 80% chance of detecting an effect if one truly exists. And remember on the last slide when we were talking about statistical significance, we want a 95% chance of making sure that we don't find an effect if one does not exist. You have to actually calculate your statistical power, and this is based on a few things. You would do a power analysis. And this is something you guys want to look for when you're looking at articles, is you want to look and see if they mention statistical power, and that you want to see if they mention that they've done a power analysis, because as you've seen in the Ellis text, a lot of people don't do this. A lot of researchers only report statistical significance, and that's actually not a good way to report their results. So you can calculate statistical power with any of these four things, and if you have three of them, then you can calculate the other ones. And so that's why they talk about doing a power analysis. Before you do any sort of research study, you should calculate power beforehand to see how many people that you're going to need to get the effect size that you want. And you should also look for this in research articles, in the studies that you're looking at. You should look to see if they did a power analysis, and you should look to see if they talk about effect size. And that's what they talk about in the Ellis text, is about how that really is best practices. It's not best practices to just report statistical significance, even though a lot of people do that. And they also talk about the importance of doing the power analysis before as opposed to doing the power analysis after. And so that's something else to consider as well. If you ever find yourself in a situation where you need to calculate statistical power, as they mentioned in the book, G-Power is a really good software that can help you out with that, and it's free. Okay, so they talked briefly about families of effect sizes, and really what you need to know is there's a family, the D family, which is differences between groups, and then there's the R family, which is relationships between variables. And in your book they have a whole list of them, and these are just some of the ones I pulled out that are the ones you will probably see most frequently. And again, just something to look out for. These are calculated in a lot of different ways, and usually SPSS will give this to you in one way or another. And so that's just something to be aware of. And what's nice to know is that, like a Pearson correlation that we've talked about, a correlation coefficient is considered an effect size, and you can see that in a lot of different places. And so that's something to be aware of as well. Okay, I want to briefly review this just to make sure that we're all on the same page. I know you guys did the application assignment last week, but just remember that an independent t-test is when you're comparing differences between separate groups. So those could be two separate groups on anything, whether it's two different experimental groups, whatever it is, and you're comparing them on one variable, right? Whatever it is, one continuous variable, so it needs to be some sort of scale variable. And then this was something that came up for you guys in the discussion on the discussion post about model assumptions. And this is something that's going to be for the discussion post this week as well, is talking about whether the article that you found, whether the researchers discussed the model assumptions or not. And this will be varied. Sometimes they do, sometimes they don't. But so these are assumptions, and that means that going in to this analysis, you are assuming these things to be true, and some statistical tests are more robust against these assumptions. And what that means, if it's robust, that means that you may be able to violate some of these assumptions and still get away with running that analysis. But there's a lot of different opinions on this sort of thing, and so that's something to be aware of as well. So for normality, is that you are assuming a normal distribution for your sample, right? And so you can actually run the Shapiro-Wilk statistic. You can run that in your descriptive statistics, and you can actually see whether the Shapiro-Wilk statistic is significant. Homogeneity of variance, I think we've talked about this before, whether using Levine's test, and that can tell you either way whether you have homogeneity of variance. And then independence, this really just means that all the scores are independent of each other, and it's not something that you could look for in your output. Independence is based on how you design your study and how you collect your data. Okay, so dependent t-test. So this is actually that paired observation. So either a pre or a post test is the most common. So within subject's design, and again, it's on one independent variable. It's the one scale variable, whatever you're measuring it on. Okay, and so there aren't as many assumptions with this because you're measuring the same people twice, but you would want normal distribution, and that the independent variable is dichotomous, and they're paired or matched in some way, and that's why the most common is just like a pre and a post test. Okay, so we're going to move on to talk about ANOVA, and if you have any more questions about t-tests or effect sizes, please let me know for sure. So ANOVA is when you have more than one group that you want to look at. So with our t-test, there were only two groups, right? There was a pre and a post, or there was this group and the other group, and that was it. ANOVA has more than two groups, and that is the main facet of an ANOVA, is that you're looking at more than two groups on a variable. And sometimes you can have, we'll talk about one-way or two-way ANOVAs when you're talking about not only more than two groups on a certain variable, so for example ethnicity, but then you might also, in addition to ethnicity, you might also be measuring poverty on a categorical scale, and so you could put those in. We'll talk about that when we talk about two-way ANOVAs. So if you're just talking about a one-way ANOVA, which it means you've got the discrete independent variable with three or more groups of levels, right? Then you have your one continuous dependent variable. Now, if you wanted to measure more than one continuous dependent variable, whatever it was, you could do that, but it would be actually a MANOVA, not an ANOVA, and we're not going to talk about that in this class, but just keep that in mind. So basically, they're looking at variance. It's all about how the data points vary, and so they actually talk about the variance between the groups. And so what they're looking for is they're looking for systematic variance, and what that means is that they're looking for a variance that actually happens systematically and is hopefully due to your intervention or whatever it is. So we're looking at that. And then they're also looking at the within group variability, and that's going to be your error variability. That's just going to be any sort of general variability that you have between your people. And so when you look at your systematic variability, and you can actually divide, and they call it the sum of squares between, the sum of squares within, and you'll find this called actually a few different things, but when you're actually looking at your output, I'll show you it's the sum of squares, and it's the sum of the squared error. So you actually calculate your F statistic, and ANOVA is considered an F test, by dividing the systematic between group variability by the within group variability. And then you would calculate it as squared, which SPSS gives you, which is the between group variability over the total variability, all of the variability in the model, all right? And so this is something to consider in your discussion when you're looking at the research article. It actually asks about what kind of F test it is. And what that means is, what kind of ANOVA is it? Is it a one-way ANOVA? Is it a two-way ANOVA? Is it repeated measures? And so that's something you're going to want to make sure you answer and talk about. Okay, so model assumptions. Again, with all of these, there's some sort of assumption. And again, you have this normality, homogeneity of variance, independence. And then here you see that this would be what your ANOVA output is going to look like in SPSS. And so you can see here, sum of squares, right? Sum of squares between groups, sum of squares within groups. Here's your F statistic, and then here's your level of significance. And so you can see here that you have a significant finding because it's below your 0.05. So you know that there is some sort of systematic difference. And the groups here are, so they received a placebo, a low dose, and a high dose. And so you can see that there is a difference between these. And they have the Levine statistic, the homogeneity of variances. And you can see, since it's non-significant, you can assume that you have homogeneity of variances, which is good. Okay, so after, and they talk about this very casually in the bullet text, which is interesting, but after you run an ANOVA, you know that the model itself is either significant or not significant, right? So you've got this F test. Let me go back here. So you have this F test, and this F test says, yes, there's a significant difference between these groups. But that's about all you know, right? You don't know exactly what that difference is. Like, you can kind of see here that there are differences, but you don't know whether there's significant differences between each other or not. And so that's why you have to look at your post hoc test. Your post hoc means after. And they have a few suggestions as to how you can look at that. And there's a lot of back and forth about what you can look at. But the ones that they suggest are Tukey and Fisher's, and I think that those can be fine. You just want to be clear when if you were going to write something up and talk about the post hoc test, what post hoc tests you used. And so what you see here is, you can see that this is an example of an output, and this is the Tukey and the Bonferroni. And what you're really looking for here, and they'll all give you something a little bit different, but hopefully they'll be similar enough that you won't get different results based on the different post hoc tests that you choose. But basically, you're looking to see, okay, so was there a significant difference between the placebo and the low dose? No. Was there a significant difference between the high dose and the placebo? Yes. So that's where the significance lies. Even though there wasn't between the placebo and the low dose, there was between the placebo and the high dose. And you see that by looking right here at the significance level. And again, we're looking at the 0.05, right? And here you see that for the low dose compared to placebo and high dose, there isn't any statistically significant difference here. Okay, and then here again, and they kind of show it again that the high dose compared with the placebo is the one that's statistically significant. And down here, even though the statistics are different, it does give you the same result. And so that's what you would report, and that's what you would look at, and then you would look at the means to really look at, say, well, which one's higher or lower. Okay, so factorial ANOVA, and they like to call these a lot of different things, but a factorial ANOVA is either a two-way or more than that. You can do several if you want. So a two-way ANOVA, and basically, again, not only are you looking at the differences among the different groups in the variable, you've got more than one variable. And so, so one of your research questions would not only be about whether there are differences between these groups, these three or more groups, but then also, is there an interaction? Is there an interaction between these groups? So here they talk about how they looked at gender and disability, and they wanted to see if there was an interaction between the gender and the disability. And so you see here that it's non-significant. There's not a significant interaction, but the ANOVA did show that there was significance when looking at different groups of disability. And so gender was not significant, but there was significance on this variable when looking at different groups of disability. Okay, and so then you can see here that this would be your post hoc to see that the disability status of the child typically developing was significantly different than physical or mental retardation. And so, again, you would look at all this and see what the main effects were. Okay, so then here's one that actually gives an example of a significant interaction. And so the same thing is that you would look here and you see that these groups, and based on group and sex, that you would see that there was no significance on these groups alone, but there was a significance based on the interaction. And they actually show this for you in your text. They talk about the different interactions that you can see, and they have the visual, which is really neat, and that is on page 149, where they were looking at, their example was a different type of therapy and whether it was given in the morning or the evening, right? And so they actually talk about how there was an interaction between those, and it actually showed that, and they looked at the estimated marginal means, and it looked like that the music therapy was more relaxing in the evening, but relaxation therapy was more relaxing in the morning. Okay, so let's move on. We're going to talk about repeated measures ANOVA. And so this is when you have, you could have measured the same participants several times on different levels. So you could do, and it could be like a longitudinal study, right? So you like measure them the first time, and then you wait 6 months, and you measure them again, and then you wait 6 months, and you measure them again. Or it can be like the example in the book where they measure them on different treatment levels, or different things that they do, and because they're still the same person being measured more than once, then it would be considered repeated measures. And again, you would want more than 2 observations, because if you only had 2 observations, you would go ahead and you would do a dependent samples t-test, right? Okay, so this is really interesting because they have the normal normality and multivariate normality, but they also have sphericity and compound symmetry. And then basically what you're saying is that you're assuming that the relationship and the covariances between the pairs of the experimental conditions and the time periods, you want all those variances to be similar, and you're assuming that, so then you would actually be able to identify any sort of non-systematic variance, right? And so you would need at least 3 conditions for it to actually be an issue. If you only have 2, it's not going to be an issue. And you can use this by evaluating Mauchly's test of sphericity, and that actually comes out when you run the repeated measures ANOVA. And so, again, you would want it to be non-significant. And sphericity can be an issue, and they talk a little bit about different ways that you can calculate things based on sphericity. Okay, so the repeated measures ANOVA, again, you would want to look at your post hoc. There's some different examples here of things you can look at as well. So that's pretty much the end of this. My hope is that by me kind of going through this, I can kind of pull out the main ideas for you guys. I also posted the PowerPoint from the text that I thought would help in addition to your reading. And I don't want to make it about getting the nitty-gritty details. I really want it to be more about you guys understanding the main ideas and actually understanding, if you're going to read a research article where they conducted an ANOVA, that you can understand what the results mean, because then you can make a judgment about how they're interpreting the results. And sometimes that you'll find in some of these research articles that the researchers will interpret their results in a way that is in a positive light, but when you really look at it, there are some major issues with it. And so it's just something for you guys to consider that. So ANOVA is all about looking at the variance between groups. So if you have any questions after this or you need any more clarification, please let me know, and then we'll also do we'll go ahead and do our webinar on Thursday where we can actually run through and do some examples of running these before your application assignment.